Okay, so in the last lecture, I want again to use the Schreiber density theorem to give evidence in that case for the Koblitz conjecture by putting that as the building block of a sieve. Okay, so I want to do some sieving, and the two things I want to show with the sieving is show that, so what I call PE twin of X, which is the number of primes smaller than X such that P plus 1 minus AP is prime. So I want to explain two results. First of all, well, the first one is not about that. The first one is about the number of prime P smaller than X such that P plus 1 minus AP is almost prime. And we can show that there's going to be an explicit constant that's the first result. So maybe I should state what is the conjecture. The conjecture is that there's an explicit constant that I wrote, and I'm going to write again because one of the nice things is to get the explicit constant. So that's the first result with a lower bound sieve, and the second result would be that the number of prime P smaller than X such that, in this case, I could have written P plus 1 minus AP is prime. This one I can show that is smaller than 10 times the correct constant. Okay. And both results are in some paper with Jiwoo. So maybe I should say that, I'm going to prove those results, and this is certainly under GRH. Okay. Which in the lower bound sieve, you need that to get some result. In the upper bound sieve, actually it influences the constant, because this constant, and this is kind of amusing, this is 5 divided by 1 minus theta, and theta is your zero-free region. So if theta equals to 1/2, it gives 10. Okay, so the better you assume for your zero-free region, you would get a better constant. Unconditionally, you will get log-log, I think. Huh? Upper bound sieve are very easy. You need to sieve very little to get something, but you need to sieve in some region. Huh? It's because when you do an upper bound sieve, you just need to remove a few primes. So I think you would get this is a question, I think you would get an extra log-log without the GRH though. It's still too short, yeah. Okay, so what about the lower bound sieve? So I think I want to start with that. So to sieve for almost prime, I'm going to use, okay, so what is Graves sieve? So the notation will be A, du, let me define everything. So let me define this weighted sum, or the Graves weight. So, of course, A is going to be the set that I want to sieve, which is P plus 1 minus AP, such that P is smaller than X. Okay. In fact, it's not going to be that. If I want to add the exact constant, I have to kick some ME in that, but let me not do it now. So if I do it like that, P will be the set of all primes for now. Okay, and what is that? I sum over all elements in the sequence that I want to sieve some weights. And what are those weights? So the weights are going to be 1 if this number looks like a prime. So what does it mean it looks like a prime? If P divides A implies that P is big. And big would be D to the U. Okay, so all those parameters are to choose. So D will be X to some power, that's my level of distribution, and U and V, are going to be chosen. So to choose. So it is going to be 1 if your number looks like a prime, which is to say it only has big prime. It's going to be 0 if there exists P divides A, which is small. And small and big would be determined to optimize thing at the end. And there's some weight which are in the middle that I'll try to write from memory, and hopefully I'll get that correctly. It's going to be the summation P divides A, and P is between D to the U and, D to the V and D to the U. And those weights are 1 minus log P log D to the U. Okay, and this means if this number is negative, put a positive number. Okay, it doesn't, once you know a number is not prime because you detected it as a small prime divisor, you don't need to continue, your weight is going to be 0. So if you look at that expression, if I wrote it correctly, when P is D to the U, this should be 0, so it should give 1. Because, if they have only big prime, it should be 1. And when you have P is D to the V, this should give 1 here, so this should give 0. So it interpolates between that. That's just what it does. Okay, so what do you do with that? Well, so when you use sieve, a lot of work was done on that, and a lot of work was done on grave sieves, and the theorem that I'm going to use is that with those optimal weight, I have that this H, A, du, dv. So now I didn't kick anything about my sequence. So this is just, the sieve that I'm using. This is going to be bigger than, and I have to define the thing. So let me write it x. Let me copy it to make sure that, here I took all prime, so my x is actually pi of x. So 2e to the gamma v of d. So I'm going to define things, but you would recognize probably most of those things, divided by u minus v. So some function. So this f of uv is just a number, and probably I have a small o of 1 because it's a weird parenthesis that I have here. Minus, and now I have my error term. So even that, it may not even be the exact thing because I think I simplified it on my sheet, but it looks like something like that. And here I have mn divides the prime dividing d to the u. And mn are some parameter to be chosen such that their product is d. And then you have number alpha m, beta n, which are just smaller than 1. Okay. So let me write something which is more or less exact, and then explain only the relevant thing in that, okay? So there's not many things which are relevant in that. So what is relevant is, of course, well, pi of x is pi of x, v of d is, so what are the two important things? Those are v of d and r of a, well, let me write d. Okay, maybe, the usual notation here, d is my parameter, let me write v of z and r of ad. Those are the important thing, and this corresponds to sieving. So I'm sieving. So what I'm doing, I'm saying, okay, which number are not prime? The one which are divisible by 2, the one which are divisible by 3, the one which are divisible by 5, and I remove them. I'm doing a sieve. And of course, the one which are divisible by 2 and 3, you should not count them twice, so you have inclusion, exclusion. So what you need to do is you need to know a of d, which is what is a of d, which is the number of a in your sequence, such that a is congruent to 0 mod d. Okay? And d is going to be square free and supported on your set P, but here my set is all prime. Okay? I need to check divisibility by prime, but I also, need to use inclusion, exclusion to, if I remove those divisible by 2 and 3, I need to add those divisible by 6. Okay? That's why I need d square free supported on the prime. And I need to evaluate that. And this is, I'm always going to write that. This is the sieve notation. Well, the size of A here is pi of x, but maybe I can write the size of A plus some error term. Okay? So in any sieve you do, this is the important thing. Okay? The rest is optimizing and, of course, a lot of work. But I need to know the number of elements in my sequence which are divisible by small primes. Okay? So, and this is, the way we write them like that. So here, normally in a sieve, maybe you expect to pick one class, omega of d to be around 1, but and the more classes you pick mod d, the more difficult it's going to be. So what do I have here? So this defines this, which is the error term. So it makes perfect sense that here I have, okay, I'm going to count divisibility, and this is your error term. Okay? And that's at the end, you'll deal with the error term. And what is v of z? Well, it's doing the inclusion, exclusion. So it's going to be the product p smaller than z, 1 minus, okay. Okay, you take all of them, remove the one which are divisible by 2, remove the one which are divisible by 3, but then add the ones which are divisible by 2 and 3, so this is exactly that. And I define my error term, okay? So it all comes from one thing, this thing. How many elements in your sequence are divisible by d? And this is put in this here.
What's R of AD?
It's the error term. Yeah, sorry. So this is this defines everything, no?
Oh, so that's capital R.
Oh, yeah, I don't know why I write capital R, yeah. It should be small r. Usually I write capital R where I don't want to care about that, and I say pile up all of those, yeah.
Okay, so the other is capital R.
So okay. So let me stick to capital R then. Okay, R and capital R are the same. Yeah. Whatever. This is the error term. Yeah. Yeah. It's good. Yeah. This is this error. Okay. So what we can show? So this has nothing to do with our application. So in our application, we can show. So I'm not going to give you the detail of that. But we can show that if I do the summation p smaller than x of, let me see how I want to write it. Just to be, yeah. Let me write it as the number of prime p smaller than x, such that p, let me use the omega notation. Okay. So this means it has less than r prime divisor, counted with multiplicity, by the way. So what is that? Well, this is, of course, simply the summation p smaller than x, 1 and 0. Let me write it in a very silly way. Otherwise. So we can show that this is bigger than this h that I defined. Okay, well, plus some error term which I can control, provided, and let me write that and explain. So provided that this thing is true, which is to say that the summation for all prime L in your interval that you're checking, so between d to the u or t to the v, of the number of p smaller than x, such that p plus 1 minus ap is, let me write it and explain it, is bounded by, okay, so here I'm going to write something x over log cube. What I mean is this is in the error term, and my main term is x over log square. Okay, so the first result that you show is, first of all, of course, there's a link between having only small, having a small number of primes and having only big prime, of course. Huh? There's an obvious link between those two. So we can show that this is bigger than that, where h is defined there with those Graves weight. What does it mean? Of course, there's nothing to show for the 1. 1 is always bigger than 1. Huh? The only thing to show is when I have a 0 here, well, it has to be bigger than that. It means this has to be 0. Okay? So you fix with those weights such that when, and maybe I should write otherwise like that. Okay? So if the number of prime is bigger than r, well, you fit with your constant such that this will imply that there will be a small prime, which makes sense, huh? But you try to do it in the best way possible. Okay? So here the only thing that you have to show is when you have a 0 here, those weights are 0. Okay? And those weights are controlled by the small prime that you have. So you can show that, but there's a condition that will pop out, which is this one. You need to know that when p plus 1 minus ap is congruent to 0 mod L square, and you're running over the primes in your interval where this is the difference between small and big prime. You know, smaller than d to the v, they're small. You can deal with them. Smaller than d to the u, they're big. And this is this interval that you have to control. Okay? So this is the first theorem that we show. So now, for this thing, you have a lower bound. Okay? So if you have that this is true, then you use the lower bound from that and you will win. But, well, what is r? And basically, when you do that, RU is equal to 1 here. Okay, that's the thing to remember. What's going to be my R? Of course, you know, the number of prime is related to their size, and basically the relation that you get in Graves sieve is that R times U is equal to 1. So of course you want to take U as big as possible to have R as small as possible. Okay, I'm not going to explain how this thing goes, but what I want to look is that provided that, this condition. Okay. So I have that the summation d to the u smaller, sorry, v is the smallest one. That's a bit confusing. Okay, what can I do with that? Well, I know that. Huh? This is, again, the Chebotarev density theorem. So I'm going to write the answer to that. This number of prime, what is this number of prime? Well, this is CL divided by GL square. Important. Okay. And I mean, the error term is critical, of course, here. So let me write it correctly. So x to the 1/2 log d log Lx. Okay. And what is the size? If you remember, let me write it like that and explain. Okay. So why L to the 6? Because I'm looking congruent to 0 mod L square. So the size of my Galois group is not L4, it's L8. because I'm into GL2 of ZL squared. So the size of my Galois group is L8. So the size of my conjugacy class, which tells you 0 mod L squared is L cubed. But then I'm using this trick of Serre that a priori it would be the size of the conjugacy class, but you can 1/2 it, which is critical. So it's good that you can do that. Okay, and what is that? So this ratio is 1 over L squared. The ratio of the size of the conjugacy class to the element of the group. So this thing is gonna be, let me write bounded. What do I have? I have pi of x summation dv smaller than L smaller than du, 1 over L squared. Well, no problem with that, It's going to be 1 over d to the v. This is certainly smaller than what I want. And then I have this error term. And then this thing that Igor mentioned, which is very annoying, I'm not going to do anything good with the summation of the error term, which usually you would. Usually you say, okay, maybe the error term is bad, but on average, you're used to work with the multiplicative group, on average, the error term is always good. It's always better than it is. But here, there's nothing that I can do. There's no Bombieri-Vinogradov. There's nothing. I'm just going to sum stupidly my error term, which is a bad thing. But I don't have the choice. So I have x to the 1/2. Okay, let me put log of x, because certainly d is given by a power of x, so I can deal with this L. And here I have L cubed. Okay, so you see the 8 popping out immediately. Because what do I get here? So this is going to be smaller than, pi of x divided by d to the v plus x to the 1/2 log x. And here I get d to the 4u. So this would give me, so when I sum that. So also you cannot use the fact that, there's no prime smaller than d to the v, but this makes sense. I mean, the maximum will be there. I mean, it does not seem that you could gain something here, but certainly you think you should be able to gain something in average, which you don't. It's not known. So if you do that, so basically you get that 4u has to be smaller than 8. No. 1/2. I'm getting 1/7, yeah. Okay, you want the main term to be smaller than, you want the error, you want this, I'm trying to get x over log square x, huh? Yeah, but I'm saying for u is strictly smaller than 1/2. Then I gain a power in that case. So any log. I don't want to deal with the log. If for u is strictly smaller than 1/2, the exponent is strictly smaller than 1. So I gain infinitely many log in the denominator. Yeah, okay, because, when you do it in the paper and you optimize, we use that. But here I'm just, I'm doing 1 minus epsilon. You're very right, yeah. 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 Let's say I could count the logs, but you need okay. Okay. Why? You know what I should have written? I should have written small o, huh? Yeah. 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 Exactly. Yeah. Okay, and I told you, so you need 4u's to be smaller than 1/2, and I told you that RU was equal to 1. Okay, which would give you can take R to S to be bigger than, 8, yeah. So 4u is smaller than 1/2, or U is smaller than 1/8, which means that R is bigger than 8. Okay, provided, I mean, this is details missing, lying here and there, but basically this is the idea, okay? And what I didn't show you, of course, was this thing, but this thing you can deal with, of course. Okay, so the thing is, you have this Shebodarev where this awful size of the conjugacy class, which puts a limit on your 8, and unfortunately there's nothing you can gain on average. So those are the two things I wanted to show you. Okay, so now if I do like that, I didn't care about the constant, and I would certainly not get the correct constant because there's this ME thing which is annoying. When I said, okay, here this thing, I should have maybe mentioned, I didn't mention it, but I'll mention it later. When you count this A of D, this depends on those Galois representation, and this nasty ME that Nathan was talking about, it will always show. Because what about the prime dividing ME? Then there would be a problem with that. So I'm going to do now a trick, and I'll do it for the upper bound sieve, because the upper bound sieve is very easy. So trick to get the correct constant. And let me do this trick for the upper bound sieve. So I want to get the correct constant, so I'm going to sieve the sequence. And this is very weird. P plus 1 minus AP such that P is smaller than X, and also P plus 1 minus AP ME is equal to 1. So it's not P which is coprime, it does not divide ME. It's this thing is, and what is ME? ME is this integer that Nathan defined, which, you know, for each elliptic curve, it tells you how pathologic or small is the Galois representation, how small is the Galois group. If you know the representation but ME, all the rest is the full inverse image. So that's this ME. So I'm going to sieve that, so my prime are going to be, of course, the prime not dividing ME. Okay, so also in the first thing, when I did the lower bound sieve for almost prime, this is what you do, but there it's not a problem, huh? Because when you do the first part, you get that this is bigger than something. Well, then removing the ME condition, it's also bigger. Okay? There's also not a problem for the upper bound, because if I look at the number of prime P smaller than X, such that P plus 1 minus AP is prime, and P plus 1, so this is, let me put it like that. This is certainly equal to the number of prime P smaller than X, such that P plus 1 minus AP prime. There's going to be a lot of writing for a very small ID, but plus the other one. So before I finish writing, you would have found what I want to show you, but that's okay. Yes?
You have D equals X to the, capital D is X to some exponent. What's that exponent?
Xi, I call it Xi. Everything is to be determined in the sieve, yeah. Everything, you know, you determine all those nasty parameters, and yeah. Yeah, you know, a lot of the details are hidden here, yeah. Yeah, okay, it will look, you don't gain by saying D is ik to the Xi, and then taking D to the U and D to the V, but you actually gain, weirdly. No, it does not seem, you know, why don't you define U as Xi times, you know, but you gain by having D a power of X, and then by doing powers of D, because they don't, in the error term, they don't play the same role. Yeah, everything is as big as it, you know, yeah. But there's, okay, I could have put D equal to X to simplify. Okay, so I'm just saying that this is equal to that. I guess everybody agrees with me. I want an upper bound, so I will get an upper bound for that. Why is it an upper bound for that? Because, of course, when P plus 1 minus AP is prime and not co-prime to ME, it means it divides ME. It would not be true if we were not looking for prime. So this thing is just, you know, numbers bounded by ME, so it goes away. Okay? So I can just get an upper bound for that. Okay? And upper bound that. And now I'm saying this thing, well, what I'm going to write? I'm going to write now upper bound sieve are a very, very simple thing. Okay? So what I'm going to do is I want to know the prime ones. Well, I'm going to remove the one divisible by small prime. And your primes can stay very small to get a result. So I'm going to say that this thing is smaller than that. Let me write it and explain. So that's the usual SA, what I want to write. What's the notation that I use? P, okay, SAP. Okay, and again, I put D to the 1. It's going to look very weird. Okay, why use D to the 1/2 and not D? There's a reason, but I could use D, but I would get confused. Okay, what is that? How do I define that? I claim that this is true, and that's a trivial thing, where, and that's the usual sieve notation, SAP D to the 1/2. What is that? It's the number of A belong to A, such that P divides A implies P is bigger than D to the 1/2. And of course, I have P belongs to P. Okay. So I'm saying the number which are prime, those are smaller than the number which have only big prime divisor, of course. I'm counting a bit more. Here I'm counting all those ones which have only big prime divisor. So this contains the prime, except of course it does not contain the small prime. If a number have a small prime divisor, it may mean that it's not prime. It also means that it is exactly the small prime divisor. So I need to add back the small prime. Okay, it's a trivial statement I'm saying here. The prime number are bounded by the one which have only large prime divisor plus the small primes. Okay, oh la 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 la. I did something. No? Okay. Okay. This I want this to be down. How come? Okay. Yeah, the board which is up is the one that I want to keep, so let me hide that one. Oh. Okay, now I need to move T3. Which one is T3? The one in front of me is, no. T3 is this one. Okay, and now what I need to compute my A of D, and this is where the trick is, so let me do it for you. Okay, I didn't tell you, I'll tell you in 2 seconds what happens for, this is as a basic sieve, it's almost a sieve of Eratosthenes, so what's happening is that I can tell you a bound on SAPD to the 1/2. Okay, just by saying, well, you take all of them, remove the one divisible by 2, the one divisible by 3, add blah, blah, blah. So this is going to be a very easy thing. And my building block that I need would be A of D. Okay, so let me compute the number of elements of A of D, which is the number of A in A, such that P plus 1 minus AP is congruent to. Okay, what is that? And here my D is square free, and also D is co-prime to ME. Because the primes in my sieve are the prime not dividing ME. So D is co-prime to ME. So let me count that. So this is the summation P smaller than X, P plus 1 minus AP ME is equal to 1, and P plus 1 minus AP. Okay, I'm doing it very stupidly. Okay, I did nothing. I just wrote the definition. So how do you detect if P plus 1 minus ME is equal to 1? Of course, I'm going to do the summation. So M divides ME, M divides P plus 1 minus AP, and the Moebius function. So this thing is either 1 or 0, depending. So it's 1 if those two are co-prime, and it's 0 otherwise. Okay, I'm using the usual detector. So if I do that, and let me flip my sum. Okay. So I'll let you. I'm doing elementary number theory, so this is very simple. I'm just flipping my two sums. And now D and M are co-prime, huh? So the number of primes smaller than it's P plus 1 minus AP is congruent mod D and congruent to 0 mod M. I can rewrite that as congruent to 0 mod DM. They're co-prime. And now I can use the Shebot density theorem to evaluate that. Okay. It's exactly as before, and as now I have this extra sum. Okay, once the number of primes smaller than X such that this is congruent to 0 mod DM, so this is this conjugacy class divided by I'm not going to care that much about the error term, but let me write it once. So log of, okay, I'm going to write log of D and O of E. And here I'm going to write what? I'm going to write D to the 3/2. Okay, why not M? Because M depends on E. I don't care about it. It should be dm to the 3/2, but M completely depends on E. I don't care about that. Okay? And let me rewrite that a bit. Okay, now, okay, those things, sometimes, when I'm at M, I don't know what they are. This is what Nathan explained in detail. But where I'm away from M, I know what they are. The Galois group splits as a direct product, the part at M and the rest. And the rest, furthermore, splits as a product over all the prime. So I can rewrite that as the summation M divides ME. And in fact, I could take the summation out, but mu M, and here I'll have CM, GM, and the part at D, actually, I can write as a product. Okay, and you know, I should have reversed my sum in a better way. Maybe I do that I'm gonna keep, well, let's take my pi of x out first of all. And my big O, actually, when I have my big O, this is out, like my big O could have been also outside of my, it was outside of my sum, huh? Because the summation m over me just depends on the curve. Okay, and my big O, you know, I don't care about it, it's outside. So, and what is that thing? And now I'm gonna write something which, okay, and now I claim that this thing is pi of x product L divide D CL over GL, and here I'm gonna write 1 minus omega of ME divided by G of ME, and I'm gonna explain what they are. I defined them last time, but plus the big O. What is the omega of ME over G of ME? This is exactly what's appearing in Koblitz constant. Okay, G of ME we know, I don't need to define that. G of ME is the Galois group, which is a subgroup of GL2Z over MEZ. So this is the Galois group. Okay, here of course, for those ones, well, this is GL2, huh? So this is the full thing, and this, all those I can compute because I'm away from ME. So, and this is what's appearing in the Koblitz constant. So recall omega of ME, this is the set of matrix in G of ME, such that the determinant plus 1 minus the trace of G is congruent to 0 mod ME. The opposite. The determinant of G plus 1 minus the trace of G is not co-prime to ME. Okay, sorry, it's in the corner, but it's not co-prime to ME. Okay. So omega and C are not exactly the same thing. C is congruent to 0, and omega is not co-prime. So this is the thing that, you know, what I'm claiming here is that this sum here is equal to that. Which seems like something you should be worried about, and which should be false, yeah. Yeah, every time I write that I worry, but this is true. It has nothing to do with saying the probability are independent. It has something to do that if I have a group homomorphism from one group to the other, the inverse image of everything has the same number of elements. This is the only thing it says. And it works only for the Koblitz constant because the condition to be co-prime to L is the same condition as to be co-prime to L squared. It would not work for the Langtrotter constant. So this is this observation that David Zewina made, that in the case of the Koblitz constant, your ME can be square free. Because you're checking coprimality, you don't need to take the square. So this is certainly part of it. Okay, so, and this is true, and this is, you know, it's just inclusion, exclusion. This is a true thing. But this is why we get the correct constant at the end. So what's happening at the end, when you do the sieve, and let me, so I'm gonna write the Koblitz constant here because I'm gonna need it. So what is the Koblitz constant? Now we're very used to those constants. At the prime not dividing ME, this is that. Okay? Because what is that? This is the number of matrix which are congruent to 0 mod L divided by the total number of matrix. So this is the probability that something is not co-prime to 0 mod L because I do 1 minus. And I have to divide, of course, by the natural probability. And then I have the part at ME, and this part is okay, the top one is not multiplicative, but the probability that a random number is co-prime to ME, this is multiplicative. There's no elliptic curve. I think first time I wrote it, I wrote phi of ME over ME, where phi is the number of divisor. But this is multiplicative, of course. Phi of ME over, it has no elliptic curve in that. So if you remember, this is the Koblitz constant, where we're kind of good, huh? Because the nasty part of the Koblitz constant we have. Or here we don't have 1 minus, but of course when we do a sieve, it's going to automatically be 1 minus. And what about this division? Well, by L minus 1. Well, when you do your sieve, I'm counting prime. I have to gain 1 over log x somewhere, which is by doing my sieve. So this is my 1 log x that I gain is here. So everything is there. So I'm going to get the correct thing. Okay, so this is the nasty lower bound sieve. Now I'm doing the nice upper bound sieve. So I think the version I'm going to write is Selberg linear sieve. So I keep telling you, remove the small prime, do inclusion, exclusion. So let me write to you, what does it mean? So why do they have different names? Because you do that, you get error term. And the different sieve is how you deal with the error term. So the one I'm going to write, so this is smaller than x. Certainly there's e to the gamma. There's no e to the gamma. Okay, and I wrote some constant that I call f of 2 plus small o of 1 plus some error term, big R. Okay? So I don't care about the error term, big R. It's going to pile up my error term. I don't want to talk about that. But this is just doing a sieve by inclusion, exclusion. If you remember, x is the size of A. Okay? And what is the size of A here? The size of A is the set of primes smaller than x such that there's a congruence condition. So the size of A is that. Huh? And again, that's not a conjecture. That's just something I just computed it. Because I took the prime p such that p plus 1 minus ap was co-prime to me. So if you take d equal to 1 and that's the size of A. Okay. And what is v of d? Well, v of d is always the same thing. This is the product, L smaller than d to the 1/2. So inclusion, exclusion. Huh? Yes, yeah. Yeah, so prime up to x is asymptotic to pi of, no, but yeah, no, this is equal. I wrote pi of x. Oh, okay, yeah, it has to be asymptotic because, first of all, this is not an integer. Yeah. Is it not an integer? Okay, let me write asymptotic, yeah. Because if I say pi of x, if I say your number is pi of x, if I say the number of prime up to x is equal to pi of x, I'm saying nothing. Huh? If I write an li of x, okay, let me write li of x, so then I won't argue with you that it's not equal. Yeah. No, to do that, I just prove you that. Take d equal to 1. Yeah, I just prove you that the size of A, if I know the size of AD, I know the size of A1. Huh? A1 is no congruence condition. Now I know this is I'm super worried that it's false, actually, even if I know it's true. This is very weird.
Sorry, I'm confused. I need to clarify. Up there on the very top board, I have script A. Maybe script A changed.
No, script A is exactly that. That's the point. Script A is the p plus 1 minus ap running over all primes smaller than x, but they have to be co-prime to me. The one which are not co-prime to me, you remove. Weirdly. It's not p does not divide me, it's the value of the group co-prime to me you remove. Not co-prime to me you remove. A is exactly that. That's the trick. That's the key point. Yeah, exactly. And the size of A I just computed here. And I computed also the size of AD, but I computed the size of A. So now if I put my sieve, you can see that, okay, maybe I won't go over the detail, but you're going to get exactly the constant. You have this, and where these things come from? Well, when I'm going to plug that, well, this thing, of course, if I let d goes to infinity, this diverges. Well, it diverges. It's Merton's theorem, huh? So what happens with that? This is equal to the product. So I'm going to do L smaller than d to the 1/2, 1 minus 1 over L, product, I lied. And I should put the minus 1 or not the minus 1? No, minus 1. Okay, I did nothing. I just multiply and divide by that. So why I did that? Because before it was a divergent product. Now it converges. And it converges, of course, to the Koblitz constant. This converges. So, and now this thing here, so, okay, I have this and I have that. And now I want to say that this is, I'm doing it in a weird way, But this is asymptotic to what? Well, this is where you gain your log. Huh? So this is Merton's theorem. I get e to the gamma, well, log of d to the 1/2, but d is x. So at the end, this is my log x. D is x to something. So the 1/2 influence my constant. Well, okay, Merton's theorem doesn't have this nasty L does not divide ME, so I have to put it on the side. So product L divides ME, 1 minus 1 over L minus 1, and the product L does not divide ME of the same thing. Okay, and now just put the two blocks together. Multiply x by v to the 1/2. What do you get? I get, so this part is the Koblitz constant away from ME. At ME, my Koblitz constant comes from this part and this part. And now I gain my log of x, of course, I have to gain something. You know, I started with x over log x. I'm sieving, I'm gaining my log of x in the denominator. And if you compute the constant that you get at the end, you're going to get 10. And I think that there should have been a e to the gamma there, maybe, yeah? Or because it's kind of weird that the Euler's constant shows up again. Okay, so this is a trick which makes you that at the end, if you put, now you see that, you know, just the constant I didn't deal with, but you see now I get an absolute constant independent of the curve times the correct constant. Okay. So I call it B, C, E, and it's not easy. I mean, this is something really, really dependent on the curve. It's in a way, it's a simple trick. I mean, there's nothing deep, but it's kind of surprising that you can get it, but you can get it. Okay, so I have plenty of time. In the time that I have left, I think that's it for that. I'm just gonna speculate wildly about, okay, I told you, okay, I can use the Chabat-Erev theorem to get evidence for the Line-Trotter conjecture, to get evidence for the Koblitz conjecture. I'm going to present two conjectures which generalize slightly those two things, and I would like to be able to do the same thing, and I will tell you where it does not work, at least for me, so maybe somebody can make it work. So is that okay for that? I'm sorry, before I should have asked that. Question? I think, yeah, I'm using the GRH, but it doesn't, you know, how long do you need for this to converge to 1 over log? I mean, you don't need a lot.
If you care about the constant.
Yeah, if you care. Yeah, exactly. So this is the question you asked. If I don't take GRH, but if I don't take GRH, I think I will still add a, you know, this would be too short and it would still be a log x popping on the top, yeah. Yeah, but if you care about, exactly, so if you care about the constant, which power of, you know, I mean, this is exactly the constant, because then you get a theta over 2 here. Yeah, exactly. So log d, you see, yeah. Yeah, this is the constant, yeah. But you can, probably you can almost see the 5 divided by 1 minus theta from that, you know. For replacing d is x to the theta, you have a 2, yeah. Exactly. So this is what, you know, because I didn't deal with the error term, but there's an error term which influenced my d. Because this work, okay, the main term converges very fast, and the biggest you take d, the best it is, but the biggest you take d, the worse it is for the error term. So the error terms tell me my theta, and my theta tells me my constant. Okay, it's not the same theta from the Riemann, yeah, sorry, I shouldn't have said that, yeah, it's not the same theta. So my eta. The error term tells me my eta, and the eta tells you the constant. Right, it's the theta, which is the zero-free region, which is 1/2. Okay. So now I'm gonna write another conjecture. Okay, so you can either work harder to prove those conjectures, or you can make other silly conjectures so you have more work to do. So I'm gonna take the second approach. I'm gonna make more silly conjecture. I mean, those ones were not silly, but maybe mine are. And I'm gonna try to apply the same tool. So this one is gonna be PL, I'm gonna call it like that. So again, I have E over Q, which is fixed, and I fix alpha a global point, which I call alpha, which is weird, but I don't want to call it P because there'll be too many P. So I'm going to look at the prime P smaller than X, such that the ord P of alpha is prime. Okay? And what is the ord P of alpha? Well, the reduction of alpha belongs to the reduction of the curve. Okay? So that's an element in the group of points of the curve. It has an ord P. And this generalized Koblitz conjecture, because if the number of elements in the group is prime, well, the ORD P has to be prime. There's no choice, because that's a divisor of the number element of the group. There's only finitely many primes such that it becomes trivial. The primes dividing the denominator of the actual point. So this generalized Koblitz conjecture, and okay, let's say I want to gain evidence for the conjecture that this thing should be a certain constant, okay, times x over log square x. That I want to wildly conjecture that, because I have reason, okay, certainly it cannot be bigger than that, because if the, so it's generalized Koblitz conjecture, so, no, certainly it cannot be smaller than that, I'm sorry. You would think maybe it could be bigger, because here I'm asking the ORD P to be prime, so even if the number of elements of the group is not prime, maybe the ORD P could be prime, but in fact, only the big ORD P will, usually the ORD P is a big number, it's going to be only big prime divisor, and it makes sense to think that this is true. Okay, it would make even more sense to think that this is true if I can show, the upper bound. Then it would tell me really I don't have too many, if I can show the same upper bound. So if I want to do the upper bound sieve, so this upper bound sieve was something super simple. I needed one thing. I need A of D, which is the number of prime P, maybe I'm going to put L, number of prime P smaller than X such that P, ORD P of alpha is congruent to 0 mod L. That's all I need. It's a very, very simple thing. So can we compute that? So again, I have an elliptic curve. Okay, it looks like a statement for the multiplicative group, but it's an elliptic curve. I have an elliptic curve, a global point, I reduce mod P, and I look when is the ORD P congruent to 0 mod L. Of course, it looks very much like all those questions that Peter was describing. And if you look in the literature, well, there's a very nice theorem by, so I'm going to put the first name, not two, Rafe Jones and Jeremy Rouse. And what this tells, it tells that if I call, if I call AL that set, well, it should be the set, huh? Okay, let me allow the set and the cardinality stands for the same thing. So the density of that set is given by, well, okay, the density of that set will be something like 1 over L, huh? This is what we believe. Well, 1 over L, when I have here for example, this 1 over L I think was L minus 2 squared divided by L minus 1 times L plus 1. This 1 over L could be, well, it comes in different form. And in that case, this 1 over L is going to be that. So if you believe everything I did before, you can do an upper bound sieve and retrieve the correct upper bound. Not only that, but it would tell you also what the constant should be. Because by doing the sieve, they would naturally appear in the constant. Okay? So what's the problem of doing that is that, and on purpose I wrote it as a density statement, is that they really prove a density statement. There's no error term. They don't prove anything about the number of primes smaller than X such that this is like that. They only prove that the natural density is that. Okay? So problem. So, no error term. Well, there's no error term. It does not tell you. Because this is the way their proof is. Because this, it looks like asking the same thing in the multiplicative proof, but actually it is not. The condition is not the same. And you cannot do the same proof. Well, maybe Peter figured out the same proof between yesterday night and now. But to me, I think you cannot do the same proof, and certainly those guys think, because their proof is way more complicated. So you have to do something else, and this something else does not go through the Shibotarev density theorem. So it does not give you things like that. Okay, so that's the first question on which, I cannot, okay. So for the Koblitz conjecture, you cannot get that much. You can get, upper bound and lower bound for almost prime, but here you cannot even get that because the basic tool is not there. And let me mention a second conjecture on which there's nothing that can be done for another reason. Okay, so here I think using the Shibotarev is very nice, but the Shibotarev needs an error term. That was lesson number 1. If the Shibotarev does not have an error term, well, you cannot use it to prove those statements. So, and let me look at another one, another conjecture. This time I want to generalize the Lange-Trotter conjecture. So I look at the number of prime p smaller than x such that p plus 1 minus ap, so it's going to be equal, let me write it to q, and q is prime. And q plus 1 minus aq is equal to p. Very cute, huh? So of course p and q has to be close one to the other, but p plus 1 minus ap happens to be a prime. And now if you go at this prime and you look at q plus 1 minus eq, it's equal to p. Okay? So there's kind of a, this is due to Silverman and Stange. Well, this is due. They're the first one who asked this question, and they call it amicable pair. Okay, because by analogy with the amicable pair over the multiplicative group. Or I can define it, and I want to define it in general because I want to give some estimates for that. P smaller than x such that p, in fact what they did is that p1 plus 1 minus a p1 is equal to p2, and then you continue up to pl plus 1 minus a pl is equal to p1. And this they call it Ellicott cycle, okay? You know, the cycle can have length L. So amicable pair is L. So L equals 1, by the way, is a case of the Lange-Trotter conjecture, huh? So L equal 2 is amicable pair. And the conjecture that they, let me put it there. Okay, they said, oh, what they said in their paper is that, oh, this should be about, you know, square root of x over log x, and this would come exactly with the same, you know, first naive probabilistic model saying, oh, the probability of a prime is 1 over log n, the probability, yeah. Yeah, perfect. Absolutely. Thank you very much. Okay, so what they conjecture is this should be about square root of x, well, sorry, x to the L over 2 over, no, square root of x over log, I'll write that. It's going to be better than writing it. But the conjecture with the precise constant and everything, that's Nathan. Okay, so they conjecture some kind of precise order, and then conjectural the precise constant is due to Nathan. And I think you did it for general L, huh? Not just for, okay. So this I'm going to call PEL of x. And here there's an explicit constant which depends on the length of the cycle, and here it's going to be like that. Okay, log Lx, you're asking for L things to be prime. So the log Lx is not surprising. And now suddenly, you know, it should be smaller than square root of x because in particular, you're fixing the first value. Huh? You know, it should be smaller than square root of x when you do that, when you do, you know. Okay, so this one looks like the Lange-Trotter conjecture. Well, first of all, it generalized the Lange-Trotter conjecture. So what you would like to do is upper bounds. So upper bounds using Chebotarev. Because I showed you, well, that's easy to get that. But why can't you get upper bound to do the Chebotarev? Because you have to look at sigma p and, I don't know how to write that, sigma p and sigma q. Because you're saying p plus 1 minus ap, that's the Frobenius at p. At the same time, you have the Frobenius at q. And you have to play with them, but there's no Chebotarev for that. Or Nathan and I thought a bit about that, and Nathan came with the idea that the Frobenius at PQ, but I don't know if the Frobenius would agree with that, you know? So we don't know how to do that. How to do p plus 1 minus ap is congruent to q, and at the same time, q plus 1 minus aq is congruent to p. Well, it means that you know the Frobenius at p and q at the same time. And there's no, so, because usually upper bounds are very easy. You just use the Chebotarev density theorem because p plus 1 minus ap is, you know, p is the determinant of the Frobenius, ap is the trace of the Frobenius. And you know everything about the distribution of the Frobenius. But in that case, it doesn't seem to work. So maybe I'll mention some results about that. So what are the results which are known about that? And I finish with that. Okay, you want evidence for that, you cannot get upper bound. So maybe you can try average. Okay, and this is due to Jim, which is here. So what kind of average result can you get? So if you go over all the curve, Okay, what you would like to get in asymptotic for an average, but there are two questions here that I'd like to mention. First of all, the first result that Jim gets is an upper bound for the average of, and Jim, you correct me if I'm saying something, of exactly the correct order of magnitude. And, okay, you're going to say, if you know a bit about that, or as Igor explained, well, this is diagonal, so you replace diagonal by vertical, I guess. And when you vertical, it's average over finite field, it's class number, well, you would lose a log. Okay? You have to work hard to gain back that log, you know, but you can do that. And you also can do that in for A, B. So notice here that, so it's natural that okay, let me write it correctly. Okay, so it's very nice that the size of this box in A and B is very thin. And the fact that the size of each box grows with L makes sense, because here you're reducing mod PQ. So the size of your box over the finite field gets bigger. So in the way that Igor explained that. So now the goal then is to take that to get an asymptotic on average. Well, you would get some constant which, you know, it should fit with Nathan's constant. This is what Jim is working on, like that. And when you do that, there's just one question is, can you do that unconditionally? So that's not something I'm thinking about, it's something that Jim is thinking about, because when you say Q plus 1 minus AQ is equal to P, I mean, so this tells you, okay, P plus 1 minus AP is equal to Q. This tells you that Q is in a very short interval around P. An interval of size square root of x, and you don't even know that they're primes in that interval. Even the Riemann hypothesis doesn't tell you that. But, so there's this condition, but there's also the fact that you're summing over prime. So it's not clear if you could get it unconditionally, but, you know, because of primes in short interval. And the reason I'm thinking that is that, for example, and now that's really the last thing that I'm writing. So if you look at another average, 1 over 4AB, summation A smaller than A, B smaller than B, number of prime. I'm not writing smaller than x because this is finite. So the Kowalski question, that there's absolutely, punctually, there's nothing. There's no trivial, I mean, the only bound which is known on that is the trivial upper bound coming from the assay bound, which is square root of n over log n, as most of the time this number is 0. Okay, if you do evidence for that, most of the time this number is 0. But you can do it on average, so let me mention that. So you can do it in average and you get, well, some constant, I don't have time to talk about that, but log n is what you should get, just because of the relative density of the primes of the integer. And you also get this thing that I cannot, which is what I call an evidence of Cohen-Landstra, because some groups, you know, among this is the number of elements of a cyclic group of order n divided by its number of automorphism. So there's a Cohen-Landstra phenomenon which kicks in there. So this is a theorem that I did with some work that I did with Ethan Smith. Okay, and this is what we proved. Well, this is what we proved assuming the correct number of prime in intervals. And what are my intervals? Of course, my intervals are n plus 1 minus 2 square root of n, or maybe I write x plus 1 minus 2 square root of x plus 1 plus 2 square root of x. Okay, for obvious reason. Because if p plus 1 minus ap is equal to n, p is very close to n.
So clearly there's some sort of condition on A and B.
Oh yeah, and also the condition on A and B are always the same. Okay, and I think, I have that. Okay, it's not in the paper, but I think, you know, because I was discussing that yesterday with Igor. So I think in the paper we have that. But I think you can do the same trick and get down to n to the epsilon. Okay, so when you do that one, you need to assume some hypothesis because, so this is a really nice thing which has nothing to do with what I was saying, and I'll stop now. Even the Riemann hypothesis doesn't tell you there's one prime in that interval. It's kind of fascinating. Of course, there's plenty of prime in that interval. It's true. It's just we cannot prove it. Even, if the size could go to x to the epsilon, there would always be the correct number of prime, but we cannot prove it. So you have to assume that, but maybe I wanted to say here, you don't need to assume that because you have a double sum. So that's the suspense. Opinions are divergent on that. For me, because in the other question there was no bypass, I have a tendency to think that it cannot be done unconditionally, but maybe it can. And I'll stop here.
Maybe it's still on the board. Oh no, it's right there. No, it's right there. You have a little point. You're counting or primes up like
Yeah, the order P is prime.
So there's this other conjecture of Lang-Trotter, which just says it's the
Yeah.
So the set of primes in that conjecture, you count the number of primes up to x such that alpha generates these vectors. So it seems to me that the set of primes that you're counting here is exactly the intersection of the set of primes that Frobenius is counting and the primes that Lang-Trotter.
But the prime that Lang-Trotter are counting is also square root of x over. Oh no, it's a density. Is it a density? Yeah.
So I believe it should be, well, okay, if your conjecture is correct, then it should be a density, and I think it is.
Yeah, I think this is correct, yeah. I think this is correct too, but I have to say that, yeah. Yeah.
So I haven't asked my question. My question is, do you have any speculation about the relationship between your constant and there?
I didn't think about that. Yeah, it's obvious that this constant is going to be bigger than Koblitz constant. Okay, that's all. There are more primes in that set. You're counting all the primes which are in Koblitz constant.
Right, so your constant is less than or equal to the Koblitz.
No, I have more primes in that. So my constant is bigger. Yeah. If the order of the group is prime, order of P is necessarily prime.
Oh, yeah, this is greater.
Yeah, exactly. So, but I didn't think about. It's true. Clearly, there must be a relation with the other Lang-Trotter conjecture, but I didn't think about that.
Oh, so what I'm saying is maybe what I said was wrong.
Okay.